Start.
You can start, sir.
So, in the last lecture, we were deriving conservation equations for mass, energy, and finally momentum. The conservation equation for mass had the general form partial C by partial T plus the divergence of the velocity vector times C is equal to minus the divergence of the flux plus any sources. The constitutive relation for the flux was the flux is equal to minus d times the gradient of C, and with that the equation reduced to partial C by partial T plus del dot Vc is equal to the divergence of d times grad C plus S. And if the diffusion coefficient is independent of position, then this reduces to partial C by partial T plus del dot and these operators, the divergence, the gradient and the curl, we had defined it in different curvilinear or Cartesian coordinate systems in different orthogonal coordinate systems, where at each point in space the three unit vectors are perpendicular to each other. So, if you have a general coordinate system with position the coordinates x a, x b and x c, okay, scale factors h a, h b, h b, h c, okay, and unit vectors e a, e b and e c, okay, such that a differential vector displacement can be written as E a into H a dx a plus E b H b dx b plus E c H c dx c. Okay. Then the gradient operator is 1 by H a partial by partial x a unit vector. Gradient operator is a vector, it is a vector operator, plus E b by H b partial by partial x b plus E c by H c partial by partial x c. That is the gradient operator that acts on a scalar such as a concentration field. Okay. The divergence operator, if you recall, del dot some vector A can be written as 1 by H a, H b, H c into partial by partial x a of H b, H c, A a. This came out of the fact that the divergence was defined as the total flux leaving a surface times the surface area. The surface area has these factors H a, H b in it. Okay, that is the reason for the divergence. And the Laplacian del square was the divergence of the gradient, okay, which was 1 a So, these operators we had derived, okay. And when expressed in terms of these operators, all these equations have the same form. If you recall, we had derived equation for the temperature field as well. Rho Cp into partial T by partial T plus V dot grad T is equal to minus the divergence of the heat flux vector, okay, minus the divergence of the heat flux vector plus the source of energy. Okay. And the constitutive relation is minus K gradient of temperature is the heat flux vector, and once I substitute that in, I will get partial T by partial T plus dot grad. So, my apologies here, this should be the divergence of V times T. Alpha grad T, where alpha is a thermal diffusivity plus Se by rho Cp. And if the thermal diffusivity is a constant, then this reduces to partial T by partial T plus divergence of Vt is equal to alpha times the Laplacian of T plus the energy source by rho Cp. So, these are the equations for mass and energy. We had derived the equation for the total, okay, density of a fluid for the center of mass motion of the fluid element based upon the total density rho. Rho is the total density. So, it moves along with the same velocity as the center of mass. There is no relative velocity relative to the center of mass. Therefore, the diffusion flux is equal to 0, and the equation for the density is partial rho by partial T plus divergence of rho times V is equal to 0. There is no diffusion part. Okay. This we can also write it as d rho by dt plus rho times the divergence of velocity is equal to 0. Okay. For an incompressible fluid, at low Mach number, where the velocity is much smaller than the speed of sound, d rho by dt is equal to 0, and the velocity just reduces, the mass conservation equation just reduces to divergence of velocity is equal to 0. Okay. So, okay. The momentum conservation equation. Before we proceed to the momentum conservation equation, we have to first express the constitutive relation for the stress in terms of the gradients in the velocity. Okay. If you recall, Fick's law for diffusion was the relation between a vector flux and a scalar concentration. The flux is equal to minus d times the gradient of the concentration. Okay. In this case, the concentration is a scalar. Okay. Therefore, the flux is along the direction of decreasing concentration, and it is proportional to the gradient negative of the diffusion coefficient times the gradient, where the gradient is along the direction of increasing, maximum increase in the concentration. We had seen those operators, okay, and their physical meaning a little earlier for the gradient and the divergence operators. The stress is the rate of the transport of momentum per unit area. It has two directions associated with it. The direction of the momentum itself, because momentum is a vector, and the direction of transport of momentum. Okay. So, if you recall, we had defined sigma with two indices as the stress is equal to force exerted in x direction at surface should be x direction per unit area at surface with outward normal in z direction. Okay. That was the definition of the stress, force per unit area in the x direction or rate of momentum transport per unit time. Okay. Force is just the change in momentum divided by time. So, it is basically rate of momentum transport per unit time per unit area of a surface, okay, with unit normal in the z direction. Okay. Similarly, you can define sigma xx as the force per unit area in the x direction at a surface whose outward unit normal is in the x direction, okay, and then sigma xy and so on. Okay. Similar to what we had defined earlier for the flux, right? We had defined the flux vector as jx ex plus jy ey plus jz ez. Okay. Because that was a vector, it had only one direction associated with it. That was the direction of transport. Okay. Jx ex and jy ey and jz ez were all the directions of transport. The transport at a surface with unit normal n, okay, j dot n is equal to flux at surface with unit normal n. Okay. So, if I have a flux, for example, if the component of the flux, if I look at it in a 3-dimensional coordinate system, okay, if I have a surface that is aligned with perpendicular in the x direction, the flux across that surface will be jx. Okay. If I have a surface aligned in the y direction with perpendicular in the y direction, the flux across that will be jy, and if a surface was aligned with outward unit normal in the z direction, the flux across that will be jz. Okay. So, these are the 3 different components of the flux, okay, with unit normal in the x direction, y and z. Okay. If I have a surface with unit normal in some arbitrary direction n vector, okay, the flux across that surface will be j dot n, okay, that is jx times nx plus jy times ny plus jz times nz, where j is where nx, ny, nz are the components of a unit vector. Okay. Similarly, I can define the stress tensor. Okay. Vector is a quantity which has one direction associated with it. In the case of the flux, the direction of transport. A tensor is something that has 2 directions associated with it, a second order tensor. The direction of the surface at which the force is exerted and the direction of the force itself. Force is a vector, a force per unit area is a vector, and the transport, direction of transport is also a vector. Okay. It can be aligned in any direction in space. So, both the force and the direction of transport have directions associated with them. So, the stress has 2 directions associated with it. Okay. So, I can write it as Ex sigma xx Ex, okay, plus Ex sigma xy Ey plus Ex sigma xz Ez plus etc. plus Ez sigma zz Ez. Okay. It will have a total of 9 components. The direction of force can be in one of 3 directions x, y or z, and the direction of transport can be in one of 3 directions x, y or z. In each of these cases, the first unit vector and the first index in all of these cases represents the direction of force. Okay. Okay, direction of force. Okay. and the second index, the subscript, and the second unit vector in all of these cases represents the direction of perpendicular to surface. Okay, the direction of perpendicular to the surface, or the direction of transport, because the transport happens perpendicular to the surface. Okay, so these are the two indices. I can also write this equivalently in matrix form. Okay, Ex, Ey, Ez into sigma xx, sigma xy, sigma xz. Okay. You can easily see that this matrix multiplication will give me back the same expression that I had for the stress. Okay. And in this matrix expression, the first unit vectors, the first column of matrix of unit this is the row matrix of unit vectors is the direction of force. The second column matrix of unit vectors is the direction of the perpendicular to the surface. Okay. So, for example, in three-dimensional space, okay, if I had a surface, okay, if I had a surface, okay, in this three-dimensional space with unit vector n, right, and it was separated into two volumes A and B. Okay. A is to below the surface and B is above the surface. So, these are two different volumes, and there will be a force exerted by the volume B on the volume A, and an opposite force exerted on the volume B by the volume A. Okay. They appear in pairs. The outward unit normal to the volume A is n. Okay. The outward unit normal to the volume A is n. Okay. And there is some force that is exerted. So, the outward unit normal to the volume A is n. Okay. And at this surface there is some force that is exerted, okay, by the volume B on the volume A, okay, at this surface. Okay. That force per unit area, or that force, okay, this force is equal to the area delta S, okay, into this tensor dotted with n. Okay. Okay. So, what you do is you have to dot the second, okay, index here with the unit normal. Okay. So, if I do that, then I will get, okay, this will be equal to delta S into Ex sigma xx nx, okay, dot the second index with n, where n vector is equal to nx Ex plus ny Ey plus nz Ez. Okay, it is a unit vector, therefore, nx square plus ny square plus nz square will be equal to 1, okay, plus Ex sigma xy ny plus Ex sigma xz nz plus etcetera plus Ez sigma zz nz. Okay. This resultant dot product is a vector. Okay. This resultant dot product is a vector, as you would expect the force to be. The force is also a vector. Okay. So, this is how you calculate the force at a surface. The direction of the force does depend upon the orientation of the surface. However, the components of this stress tensor, these 9 components, do not depend upon the orientation of the surface. They are uniquely specified at each point. Okay. Okay, similar to, for example, the transport rate across a surface of mass, say, does depend upon the orientation of the surface, but the flux vector does not depend upon the orientation of the surface. In a similar manner, the force exerted depends upon the orientation of the surface, but the stress, the components of the stress, the 9 components of the stress, do not depend upon the orientation of the surface. Okay. Similarly, if I had a surface, for example, aligned with the unit normal in the x direction. Okay. If the unit normal were in the x direction and there would be some force at the surface F vector, okay, then that F is equal to delta S sigma dot Ex, okay, which will be equal to delta S into Ex Nxx, sigma xx plus Ey sigma yx plus Ez sigma zx. That will be the force that is exerted at that surface. Okay. Yeah. Also, the point to note is that this F is the force exerted by the surface, by the volume B on the volume A, that is the force exerted on the volume whose outward unit normal is in the x direction. Okay. In this case, A is below and B is above the surface. So, this is a force exerted on the volume A by the volume B. Okay. Now, for the volume B itself, okay, the outward unit normal is in the minus n direction. Okay. For the volume B, the outward unit normal is in the minus n direction. Therefore, the force has to be the negative. Okay. So, the force exerted on the volume B, force on B, is going to be equal to delta S into sigma dot minus n. Okay. Because the outward unit normal to the volume B is inward to A. So, it is equal to minus n, okay, which is equal to minus the force on the volume A. Okay. And this is required for consistency with Newton's third law, that forces on if exerted by one volume on the adjacent one has to be the negative of the force exerted by, okay, in the other way. Okay. So, this satisfies that relation. Force can further be separated into 2 components. Okay. The normal force, which acts perpendicular to the surface. Okay. Normal force is equal to n dot F, okay, which is delta S into n dot sigma dot n. Okay. Note that sigma has 2 directions associated with it. Okay. Sigma has 2 directions associated with it. Okay. And therefore, if you take the dot product of 2 directions both with the unit normal n, you will get a scalar. Okay. And this is the normal force Fn. Okay. Okay. So, this acts in the direction perpendicular to the surface. Okay. The normal force always acts in the direction perpendicular to the surface. Okay. So, when you take n dotted with this force F, you will get a contribution that is along the unit normal. Okay. And then there is the other force, which is sometimes called as the shear force, okay, which is equal to the total F minus the normal force. Okay. The component of the normal force is Fn, okay, and the unit vector is n. So, the vector normal force is Fn times n. Okay. This is delta S into sigma minus n dot into n. Okay. The difference between the total force and the force normal to the surface. Okay. I'm sorry, I should write the sigma dot n here. Okay. So, that would be the force that acts parallel to the surface, okay, with unit normal n. Okay. Okay. So, this is the definition of the stress tensor. Okay. This is the definition of the stress tensor. It I wrote it for you in this form. Okay. I wrote it for you in this form. Okay. Very often we do not write the left and the right unit vectors. Those are understood. Okay. Those are conventionally considered to be present. Okay. And we just write it in matrix form. Okay. This is the way in which the stress tensor is traditionally written, okay, in a matrix form. Now, once again the stress tensor is a tensor. Okay. So, for example, the flux I told you was a vector. Okay. It has a magnitude and a direction associated with it, and of course, the components of the flux vector will depend upon the coordinate system that is used, okay, because you are expanding the flux vector in unit vectors along the coordinate directions. So, if you rotate the coordinate system, for example, the components of the flux will change. Okay. However, the flux itself is a vector at a physical position in space, which has an identity separate from the coordinate system that is being used to analyze it. At each location in space, where, for example, the concentration or the temperature field is defined uniquely at each point in space, the gradient of that field is also a vector which is defined uniquely at each point in space. Therefore, the flux vector has an identity that is independent of the coordinate system that is used to analyze it. Similarly, the stress tensor is a tensor. It has two directions associated with it, the direction of the force itself and the direction of the perpendicular to the surface. And this also has an identity that is separate from the identity of that is independent of the coordinate system used to analyze it. Okay. It has an identity that is independent of the coordinate system. It's an object which is independent of the coordinate system, and it has two directions. And because it is independent of coordinate system, there are certain invariants of this which do not change even when you change the coordinate system. For a vector, for example, the invariant is the magnitude. Okay. The length of that vector is independent of the coordinate system that is used to analyze it. In a similar manner, the stress tensor also has an identity that is independent of the coordinate system that is used to analyze it. So, we will discuss a little further the form of the stress tensor, which I have written for you in matrix form, and analyze that and draw some conclusions about what is the nature of this matrix, the stress tensor that we analyze, before we go on to trying to relate the stress tensor to the gradient of the velocity in a constitutive relation. So, I have defined for you what is the stress, the components of the stress, and how they are calculated, and I have written out for you this in matrix form. We will continue this analysis, examine angular momentum conservation as well as the normal and the tangential parts of the stress before we go on to analyze the rate of deformation tensor. I will continue this in the next lecture. I will see you then.